So welcome back. This is the lecture on function approximation for machine learning. So this has developed only over the last year and might be a little bit preliminary, work in progress. Although I think it's quite finalized. Just to warn you a little bit. So in an actual application, the data scientist needs to decide which model to use, like linear perceptron, fixed basis functions, neural networks, kernels, whatever. And there's one issue is how well is one doing in the actual problem with the data actually available. And this will be covered in the lecture on model selection, and where we learn about some empirical methods for analyzing some of these issues. But what can theory tell us about these issues? Why are, for example, deep neural networks so successful? So in this lecture, we will be a bit informal, since the formal treatment require advanced mathematical frameworks and are beyond the scope of this lecture. So I'm reviewing main results. So first, we have to consider a target function class. So let this calligraphic T be a set of target functions. And the question is what characterizes this function that mother generates for a particular problem, for example, image analysis or image classification, and how can I characterize this class. So the target function is the large blue circle in the Venn diagram. In a theoretical analysis, one characterizes this class in some way, hopefully limiting the class to the one actually occurring in practice. And it should be not smaller, because then you're missing something, but it should also not be much larger. You don't want to be able to model things which never really occur in the real world. How does one define this target class? Often using some degree of smoothness of the function, or another class of functions are composable functions, for example, which are important for deep learning. But we are mostly dealing with smoothness. The modern view is that the target function class assumes a tiny space of all functions. For example, deep learning models work so well because they match this class reasonably well. That's some people work on this assumption and develop theories here. Some claim that machine learning is impossible if the target function class is not restricted in some way, and sometimes this is referred to as the no free lunch theorem, which means that in the US or in other countries, if you get somebody invites you and pays for lunch, typically this person doesn't do it because he likes you. But there's some second thing behind this, some hidden cause why this person invites you for lunch. So there's no free lunch. Even if you have a free lunch, somehow you have to pay for it in some way. So this is the huge space of all possible functions, and the actual target functions realized in nature is assumed to be a small part of that. So what characterizes the model function class? So we have the target function class, which is what we're trying to model, and then we have some models available, and we call it model function class M. So it's characterized in the next slide by the large green circle. And just to simplify matters, mostly for notational simplicity, we assume a model function can be described as all functions of a particular form with a parameter vector, and by varying this parameter vector, we get different members of this model class. And one thing we are interested in is the worst case difference between the optimal one out of this class and the actual target function. So let's first maybe look at the picture before we discuss the other slide. So here, the blue one, the left side is the target function class, and it's much smaller than class of all possible functions. And this green circle here indicates the model functions. And so in this example here, example 2, the target, the blue one, can be modeled also by the model function, by a member of the model function class. And so they can completely overlap, and everything is great. We have one member in our model function class which provides a perfect fit to the target function. So here it looks a little bit worse because there's not complete overlap. There's some functions here, the blue one, which cannot be modeled by any function out of the model class, and we are interested in this epsilon. So what is the largest distance, the worst case situation of a function which can be fitted by a function from the model class. So this is the model class, is the target class. What is the worst case epsilon in this situation? So the blue one is a target function, the green one is the closest function from the model class, so FW opt. That's the situation. Yeah, so we discussed this already. So this is maybe more the typical situation. You have a target function class, and your model function class is sort of smaller because maybe you don't want to have a model with so many parameters which are difficult to fit based on the data. So often in reality it's a little bit more complex than the models you are assuming. In that case, it's important that this epsilon is small, and you want to make some statement about how big this epsilon is. So what is the worst case difference between a function from the target class and the best function from the model class? And so this is the best function from the model class. So this is what is approximation theory, and that's what we are concerned about in this lecture. There's also another issue. So the red dots in the next slide indicate the current estimate based on n training data points. And a statistical analysis, for example, classical statistical analysis, Bayesian analysis, or statistical learning theory, and some others make a statement about the statistical error, which is the distance between the red dot and the green dot. And with increasing number of training data points, the red dot should move to the green dots if you have a good learning algorithm. So for example, for model class of fixed basis functions, the statistical error is proportional to the number of basis functions divided by n. Thus, the statistical error increases proportional with the number of free parameters and decreases inversely proportional with the number of data points. And this will be discussed also in future lectures in more detail. And if you're interested in the total error, typically, roughly it's the sum of the two errors. So here's the picture. So we have our targets again, our best fitting models from the model class, the green one, but based on finite number of data, we haven't reached this optimal situation yet. We are somewhere in this space, and there's a difference between the best model I can do from the model class and the current estimate of my model. And this is called statistical error or variance, and it's the distance between the optimal model out of the model class and the ones which I'm currently estimating. And this we will discuss later, so this is not so much the concern of this lecture. We are more concerned with the blue distance. And there are other issues which are often related to these model class issues. There's computational complexity. How long does it take to train the model? You don't want to wait forever. Are there local optima, which we also will discuss in more detail later. Here's an example for systems with fixed basis functions, which we have already discussed. The required computational scalars number of basis functions to the power of 3. I think we mentioned this in the lecture on linear regression. And in this situation, there's no local optima. So these are the results we are looking for. And there's computational complexity in prediction. How expensive is a prediction? Some models can make a prediction very quickly, like neural networks, and others are quite expensive also when they're used in prediction, like kernel systems. And then there's memory complexity. The question is, how much computer memory do I need during training and during prediction? You also don't want to waste a lot of computer memory depending on the application. So what is this distance between function? So this is a definition. So consider two functions f and g, and we look at the integral. So we consider the difference between f of x and g of x, and we consider the square of that expression, so it's a squared error, and we integrate over some region input space. Typically, we consider a unit ball, so that's a ball around the original with a distance of 1 in any direction. And the ball is in m dimensions, and VB is sort of the volume of that ball, whatever that is. So it's sort of the average error we are producing. And of course, if your data is outside of this ball, you can always normalize the data to be sort of in this ball. So it's simply the squared Euclidean distance applied to two functions. And with this definition, the approximation error is the distance with respect to this ball between f, so the true function, and the optimal one from the training data set. And we also define this epsilon to be the worst case of this. So the worst function f, which gives you the largest distance. So we're looking for the smallest distance, but there's some worst case. The worst f for which the smallest distance is pretty large. And we can also use this distance measure to look at the statistical error. It's the distance on the ball between the optimal f and the current estimate, the function with the current parameter estimate. So this is the distance between functions we're interested in. Sometimes we introduce also this p of x in this integral. That just means that if p of x, so in regions where there are a lot of data, we should have a larger weight, and in regions with no data, we don't really care. So we can also look at it, I mean, we can transform it to this other measure with the ball. If we say the data is uniformly distributed on the unit ball, then these two things are the same. But sometimes it's more important, it's also important to consider that that the input data might really be restricted. And we will discuss this later today in this lecture. So sometimes input data only occupies a small subspace, the manifold of this unit ball, and some learning approaches are able to explore this. So we already did in the lecture on fixed basis functions, a first analysis. So let's consider an input space of dimension m. So we have m inputs. And if in one dimension we need a of these RBFs, in our example, maybe a equals 10, and we want to maintain the same complexity in higher dimensions, we need a to the power of m RBFs and m dimensions. So that was discussed in the lecture on basis functions. And here's the plot. So in one dimension, we need 10 of these RBFs. If we want to assume the same sort of smoothness in a high dimension, we need 10 to the power of 2, which is 100 RBFs. So this tells us how many basis functions we need. So if m phi is the number of basis functions on the order of a, so the number of basis functions per dimension to the power of m, which seems to indicate that the number of basis functions increases exponentially with the number of dimensions, which is bad. There are also relationships to other concepts for the advanced experts. The number of basis functions plus 1 is also called the VC dimension for this model class. It's also related to the entropy concept. The notation is VC dimension of the model class. And 2 to the power of m phi is the number of distinct classifiers that can be realized or shattered. So it's sometimes called the shattering dimension. What we're really interested in is the approximation error. Here we introduce the parameter small m, which characterizes the smoothness of the target class. So if you have a large m, the target function class is very smooth. If you have a small m, the target function class is not very smooth and contains a lot of high-dimensional components. So in this theoretical work, for example, m can be the set of all functions with m inputs with continuous partial derivatives of orders up to m. So the discontinuities sort of occur in higher dimensions, and the low dimensions are all very smooth. So just think of it as a smoothness parameter. Then one can set this epsilon, so the error is of the order of 1 divided by a to the power of m. So this is derived in these works on approximation theory. So a is our a, the number of sort of basis functions per dimension, and m is a smoothness parameter. And this means the error is small if the right part in this bracket is large. So if a is large, so we have a lot of resources, the approximation error goes down, and with if m is large, so if the target functions are smooth, then also the approximation error is large. So it's a very intuitive equation. And we can plug this equation into this equation, and we get, and this is a main result, the number of basis functions on the order of 1 divided by epsilon, so the error we are willing to tolerate, to the power large m, so the input dimension divided by m, the smoothness. This result can, for example, be found in the paper Why and When Can Deep but Not Shallow Networks Avoid the Curse of Dimensionality, a review by Tommaso Poggio and co-workers, and it's published in the International Journal of Automation and Computing. So let's assume epsilon equals 0.1, so we want to have an error of only 0.1. Then the number of basis functions is on the order of 10 to the m divided by large m divided by m. So the number of basis functions increases exponentially with this quotient large m divided by small m. And then there are different cases, of course. So if m is large, so the number of input dimensions is large, and the smoothness is low, so that's very unsmooth function, then a large m divided by small m, which is in the exponent, is large, and m phi, the number of required basis functions, is exponentially large, unrealistically large. And this is the famous curse of dimensionality, and this was really for many years a showstopper, and people thought, partially at least, that trying to model functions, nonlinear functions in high dimensions is completely hopeless. Okay, first of all, it turned out there are other cases, and then it turns out that not all, in all situations where m is large and m is large m is large and small m is small, we cannot. Sometimes we can avoid this curse of dimensionality, as I will discuss. So here, so this checkerboard pattern, let's say, exists in 20 dimensions. I'm just showing it's sort of a slice through this space. So the m is large. So this is supposed to be the target function. So small m is large, and m is low, small, because it's very high frequency function, but a large m is high. So the required number of basis functions is in fact huge here. And this is the curse of dimensionality. So case 2 I call the blessing of dimensionality. So if m is small or not too large, so the input dimension is relatively small, but m is small, so the smoothness is small, then if you divide a small number by another small number, it might be acceptable. And this is, so we have relatively small inputs, but high complexity. And this is what I call the blessing of dimensionality, because as we learned in the lecture on basis function, we can transform our relatively low dimensional input space to a high dimensional basis function space, and then we can solve it with a linear classifier regression system. And by transforming a low dimensional problem into a high dimensional problem, things become simple. That's why I call it blessing of dimensionality. So here m is supposed to be 2 dimensions, so x1, x2. Complexity is high, so smoothness is small, but 2 divided by the small number of smoothness must still be acceptable number. Case 3 is m is large, so we have a lot of inputs, but m is also large. So we have a very smooth function. For example, a linear function or a function which is close to being linear. We discussed this already, that in high dimensions the target functions are often very smooth. If, for example, the target function exhibits voting behavior, each input has a small contribution to the output. Or in particular, if you consider linear functions, then m phi equals m plus 1, and target functions can be well approximated by linear functions, and the input dimensions is allowed to be quite high, sometimes of the order of 10,000. Nearest neighbor method, which you might learn about in the lecture on KDD in detail, still would possibly have problems. And here we see a little bit the advantage of training discriminantly. Of course, neighborhood models can also be fixed by learning an input dependent distance metric. But okay, let's not focus on that. The important thing is a neural network type or a basis function system or even a linear system might be able to give you a very good model if the input dimension is large, but also the smoothness is large. And then there's case 4, which I call simple. So small m, so small dimensions and large smoothness. Of course, that's a very simple case and can easily be modeled. So this is maybe shown over here. Only 2 dimensions and it's smooth, so any simple system can model this. So case 1 is the terrible one, really. So we already got 3 good situations. But even case 1 is not as hopeless as it first appears. since in reality classes are more restricted. And there are two important situations. The first one is that the target function might have high frequency components, but they are only local in some sense, and a sparse solution is feasible. This is where classical neural networks can work quite well. Then 1b, we are looking at this input data distribution of x, so P of x, and this might be really restricted to a low-dimensional manifold, and some learning approaches can really exploit that. And the third situation is the target functions are composable, and this will be discussed in the lecture on deep learning. So not today. So we have case one again, a large input and small smoothness. So M phi is very large. But in this situation, only a small part of these M phi's have non-zero weights. So almost all M phi's drop out of the equation, which means that the high complexity might only be limited in a restricted region in input space, or might be restricted in some other way. Sometimes the number of non-zero weights, or the number of basis functions with non-zero weights might even be independent on the number of input dimensions. And this is something where neural networks can work quite well, because the classical neural networks, because they sort of search for they adapt the basis functions in a way they search for the optimal set of basis functions. Whereas if you start with fixed basis functions, you cannot really do that. So in a way, classical neural networks, which we will cover next, are sort of basis function systems where the basis functions can be learned. And then we need h can be much smaller number than mh. And this was, in fact, I think in my understanding, the main reason why neural networks also in the 90s, 80s and 90s worked surprisingly well and were quite high-performing systems. So here in this case, we have high frequencies, but they only go in this direction, and a neural network could exploit that. Whereas a system with fixed RBFs and no pre-processing and pre-analysis, you would have to place a lot of resources everywhere. So the second case, 1b, is the situation with a manifold. So far we did not assume any particular input data distribution. P of x might be uniformly distributed within the unit ball. But sometimes P of x is restricted to a subspace of small dimensions called M sub h, which might be very much smaller than M. And if this subspace is sort of nonlinearly formed, then it's called a manifold. This is often the case, for example, when model accuracy is very high, for example, OCR, you get a very small classification error, and input data is probably on manifolds. So in the equations, instead of m divided by m, so large M divided by small n, we can use large M sub h divided by m, and this manifold dimension might be much smaller than large M, and M phi, the number of basis functions required, might be much smaller. But this is also something which neural networks can exploit quite nicely, and deep learning and deep neural networks, and we will cover this in the coming lectures. They, for example, have the ability exploiting that. But you can also use any model if you do pre-processing, for example, clustering or principal component analysis or independent component analysis, to first find this manifold in a form of dimensionality reduction, and then apply any model class of choice. So you can also do sensible pre-processing or dimensional analysis of the data, and then you can use these methods as pre-processing step. So here's an example. So the data is in 2 dimensions. The map itself is quite complex, but if the data is only on this 1-dimensional ellipse, then this is really the dimension which matters, and we don't really have to model all this stuff outside of this manifold. This would be, so this is a subspace. This would be a manifold. So you have this, so it's linear, small. If you only move a small distance, it looks like a linear subspace. It's called then a manifold. So sometimes the data don't live in this linear manifold, but on a nonlinear manifold, and it's a very common situation in practice. So you might question, why does nature generate data on a manifold? We sort of encountered this already in the lecture on basis functions, but in a little bit different way. So there we said nature gives us this data on X, and we artificially transform it into this basis function space, and then data they are really placed on this manifold here. This is a manifold. But you can also maybe think that nature did this. Nature has some inherent low-dimensional representations, X, but nature already transforms it into this high-dimensional space. And so nature gives us this data on this manifold. So that might be a nice intuitive way of understanding why a lot of data in the input space for us, after nature did this transformation, looks like data is on a manifold. But there's a danger. If you consider test data outside of the manifold, then performance might degrade quickly. So for example, here we might have a very nice model for data which are also positioned on this linear space here, but if we go orthogonal, the model doesn't really know anything, and it might really predict pretty badly, and that's these adversarial examples you might have read about in the news. So this manifold understanding gives you a good understanding, a good feeling for why this is really happening. So although if you model or analyze this epsilon distance on the actual training data, this might be really nice and small, but if you then take the same model and analyze it on the ball, it might be really large. Sometimes this problem is also called covariance shift. So covariance is another name for the inputs, so which means that this distribution in the test data is not the same as in the training data. So if it's here, then we might have a problem. So that's another name for this issue. So in conclusion, basis function performed a nonlinear transformation from input space to basis function space to avoid the curse of dimensionality. The curse of dimensionality, large m divided by m, should not be very large. Null networks are effective when the basis is sparse, because the nonlinear adaptation in neural networks can find this sparse basis, or when data is on a manifold. And now we want to compare a few models with different situations. So here on this axis we see the different cases we discussed, and here we see different models which can be applied to these different situations. So if we look at the linear model, first of all we can observe that if we have situation 1, m, large m divided by m, small m is large, then in fact this really occurs and no approach can really handle this. Nothing can be done. So then if we look at the Blessing of Dimensionality, so small input space, but high complexity of the function, the linear model cannot do much because it cannot deal with this complex mapping. Neighborhood solutions, also discussed in the KDD lecture, might perform quite well because the nearest neighbor might be quite meaningful. Systems of fixed basis functions might also perform very well. That's what we discussed in the last lectures. Neural networks typically perform well. Deep learning performs well, and kernel systems also perform well. If the function is high dimensional but smooth, linear functions perform quite well. Neighborhood methods might run into problems because the nearest neighbor might not mean much in this case. Systems with fixed basis functions, if you consider smooth basis functions work well, neural networks work well, deep neural networks work well, and kernels also work well. And of course, in the simple case, also all methods work well. Then we have 1a, so the situation, high input space, but small smoothness. So linear functions cannot exploit that, neighborhood functions cannot exploit that, fixed basis function approaches cannot exploit that, but neural networks can sort of find the right basis by adapting the neurons in the neural network, and similar with deep neural networks, and kernels also cannot really exploit that necessarily very well. Okay, then data is on a manifold. Linear systems cannot exploit this. A neighborhood and fixed base function cannot exploit that unless we do some dimensionality reduction as preprocessing, clustering or PCA, which I mentioned. Neural networks have a good chance of finding and exploiting this manifold. Deep neural networks have the same property. They can find and exploit this manifold. And this is also a big plus for kernels because they are also only placing resources in areas of the input space where actually data occurs. So this is probably the reason why kernels were quite high performing. So kernels we'll cover this later. That was the approach between the 90s, 80s, 90s, hype on neural networks. Before deep learning occurred, people were using kernel-based systems. And the last class, which we will discuss in the lecture on deep learning. Deep learning has a big plus here because it can exploit this particular structure in the function class by having defining an appropriate model class. So thank you very much. This was the lecture on approximation theory. Thank you very much.